So let's talk a little bit about what typical patterns we see in enterprise networking today. So usually when we go into a typical deployment, we see a network, right? And inside that network, we have services, A, B, and C. And these things talk to each other, as you would expect with services. And then at the edge of this network, there's some kind of big reverse proxy implementing the ingress pattern. Traffic is coming from the outside world and is being routed to various services within the network. And this is the typical pattern we see today in enterprises. Or at least it was, and we've seen how this evolves a little bit. So one of the first problems is obviously, you have the outside world and people want to connect to your services, and you need policies to control how they do this. And so what we see is people adopt solutions that are typically known as API management solutions. And these solutions provide things like rate limiting and detailed controls for access and authorization, and different support for access control mechanisms, and a very, very long list of services all the way down to kind of logging and billing, because they need all these controls to control external consumers consuming your services. And this has been a pattern in the enterprise for almost 30 years in some ways. Then what we started to see in the industry, right, is the big boundary control around the network was what we assumed would be the security boundary, right? My insiders were inside and my outsiders were outside. And so if I wanted security, I would just make sure that I had all the security controls at the edge of my network. But the industry rapidly learned that it's very hard to keep everything at the edge of the network, and boundary controls don't really work. So we ended up in a world where we had insider threats, unhappy actors inside your network. And if they were inside your network, then because there was no protections for any of the internal access, they could just go directly to some service, do whatever they wanted, and you had a giant security breach. Right? And so the industry has learned over the last 10 or 15 years that insider threats are a real issue. And so we need to have controls now inside the network to fix this problem. And this is where the whole basic principle of zero trust comes from, that for any given communication path, we want to make sure that we enforce access control on it, and that we don't just assume that all access paths that are internal are safe. So what did we do? Well, we had all this policy capability living up here in the API management layer, and that policy included access control. So why not reuse it? So we said, let's just send all the internal traffic through the ingress. So we adopted this pattern, which we kind of commonly or colloquially call hairpinning, which is we send what was now all the internal paths, they all loop back around and they all come in through this big ingress proxy. And now we get all the value, all the policy controls that live here. That's a different kind of problem though. Yes, we have a lot of policy control. And as long as we can enforce that nothing internal can talk to each other without going through this thing, then we've achieved a reasonable security posture. But it faces two major problems, right? One, what you pay for and the amount of traffic that goes through your API management product, generally you're paying for the amount of traffic. And usually internal traffic is orders of magnitude more than external traffic, right? It can be a fan out. And so it becomes very expensive. The second problem is there's just one of these. It's a single point of failure. And so if B needs to talk to C and they have to go through this, and for some reason that doesn't work anymore, then nothing is talking anymore, right? And we know from experience that big single points of failure in large distributed systems are really, really problematic, right? And so we have a SPOF. And there's a kind of related issue with this is, well, if this is distributed across lots of physical locations, but this only runs in one place, then not only is it a single point of failure, but it's also a kind of single locality choke point, and it can be very expensive to get your network traffic to it and from network traffic to come back to the services from it. And so it can add a lot of latency. This pattern is really common. This is probably actually the most common pattern we see in enterprises today, trying to implement zero trust and security postures. So it's into this world that service meshes came. We're like, okay, well, we want all of the policy capabilities that live at this layer, right? This offers us rich policy control, But we don't want these properties, right? We don't want high latency, we don't want a single point of failure, and we don't want it to cost an arm and a leg. So how do we go about doing that? Well, basically what service meshes did is they adopted something called the sidecar pattern, which is to inject proxies into these network paths and co-locate them with the applications. Now, by distributing these proxies into the network, into these applications, we solved the single point of failure problem. We also largely solved the latency problem because it's basically physically co-located with each of the points in the communication. And so when they talk to each other, there's no large network round trip that has to occur. And because we use commodity infrastructure, the cost is way, way lower. And this also scales much better, right? Because it scales with the applications, the number of instances of the applications, so on and so forth. So this is definitely better, right? Service meshes and the sidecar pattern radically improve over the kind of hairpinning pattern. But that's not to say they don't come without their own problems. These proxies that we inject into the network, we're really injecting them into the application, which means they live with the application. If they need to be upgraded, the application needs to be upgraded, right? And so they kind of live in this hybrid world of responsibility, even though they live in the application, but they're kind of logically owned by the platform or infrastructure team. And so if I need to perform an upgrade, that means I have to do a rolling upgrade of all the applications in the fleet. That's not always the easiest thing to do. And as we've seen over the years, getting organizations which have problems doing rolling upgrades of their applications or their whole fleet can be very hard for them to perform an upgrade of their service mesh. Also, we have to load a lot of capability into each one of these proxies. There's a control plane that's distributing configuration to them. They have to know a lot about the topology of the network. Because there's a lot of policy capability that lives in these proxies, they need a lot of configuration to perform their policy functions. And so they can become quite bloated in terms of resource footprint and resource consumption from CPU and memory standpoint. And so, in Istio, we've been doing this for about 7 years. This is the dominant pattern in service mesh land. But over the last 3 or 4 years, having learned a lot from seeing these types of patterns deployed in production, we challenged ourselves to think about what we could do better. And so we spent a lot of time thinking about this and getting feedback and looking at, well, okay, is there a better pattern for achieving the same logical effect, right? Which is we want security, we want policy control, we want dynamism and flexibility, but we want a much lighter operational model. And this is why Ambient Mesh and the Ambient Mesh pattern was born. So if we look a little closer at a typical infrastructure, in the Ambient Mesh world, right, we have a node, just like you would, and then we have an application, let's say A, and another application B. And instead of injecting sidecars into them, we run a piece of infrastructure on the node as a daemon that we call ztunnel. And it has permissions, because it runs on the node as a daemon, to be able to capture the network traffic going into, out of A and B, much the same way that the sidecar would, but it does it without having to run inside the application, and it can do it dynamically. So all of the traffic into and out of these applications is now routed through the ztunnel, right? And we can do the same on another node. And the same pattern applies here. And the control plane for this system basically tells the ztunnels how to route traffic between all these instances of the applications, and so we can have traffic flow. Ztunnel does a very, very small fixed set of things. It doesn't try to implement all the policy controls that we have over here. It is an L4 thing, right? And so it's very mechanical. It implements MTLS so that we guarantee that we have compliant security for all traffic that's flowing across nodes, and also for traffic between applications on the same node. We use the same communication patterns for all of these things. And there's a control plane telling it how to route between A, B, C, D, and E, just like we have in Sidecars. But there's one other thing that it knows how to do. We introduce another pattern, which we call the waypoint pattern, which is really the L7 capability of the service mesh. But it's now running as a proxy that's scheduled into the network. And so I can say that this waypoint is the waypoint for A. If you want to talk to A, traffic must go through this. And we control that, we declare it into the infrastructure, and now ztunnel knows if I want to send traffic to A, I'm going to do this. And you can do this dynamically, right? I can dynamically create a waypoint for A or for B or any of these things, and I can add them or remove them, and at no point do any of the applications have to restart or change. And then all of the policies, the rich policies that we had in here, like quota and rate limiting and everything else, and advanced HTTP routing and all those other features are now loaded into here. And so we get all the same capabilities, right? All the same policy controls that were here are now available in this system. I could just start with ztunnel and I would get the L4 and security authorization properties at that layer. And only if I want L7 features can I enable the waypoint, and then I get all the additional L7 capabilities. But at no point did the application change. No application team had to perform some operational task to upgrade any component in this world. The operations team, the team that owns the platform, owns the ztunnels and owns the infrastructure that runs the waypoints. This yields a lot of flexibility. Right? The waypoints, because they run in the network now and not associated with the applications, can scale to the amount of traffic going into an application, not for how many instances of this application there are. So I can have waypoints that handle lots and lots of traffic, even though there's a small number of applications, or I can have lots of instances of the application and a very small number of waypoints. And generally what we see in production, the average number of instances of any given application, what we've seen typically is about 7. And they receive, somewhere in the order of about 100 to 500 RPS, and one waypoint instance can handle all of their traffic quite easily because they're very efficient. We use Envoy for this. And that yields a massive resource saving because over here we had to have basically 7 instances of Envoy fully configured with all the policy to do everything that we wanted, and here we need to have 1. And because ztunnel is so cheap, it's basically a marginal cost to your infrastructure, we yield a huge resource saving. So we have the operational saving because we no longer inject things into the applications, which means we have better upgrade cycles. We now have a big resource saving. And what we typically see is an order of magnitude cost saving versus the sidecar model in production systems, sometimes more than that. And then the third feature that we get is that this is dynamic, right? I can have L7 when I want it, when I don't want it. And I can also have different implementations of the waypoint when and if I need them. And we at Solo support the ability to take our Glue Gateway product and inject it as a waypoint into the network, which means that all of the additional policy controls that we build into our API management product are now available for east-west capabilities in the service mesh architecture. And this is a really powerful pattern and part of our Omni Gateway strategy, which we'll talk about more later. So if you're using Sidecars in production today and you're interested in getting to the ambient mesh pattern because you think it's going to save you a lot of resources or you're interested in the operational improvements, then go to ambientmesh.io. We have a lot of resources there that will help explain to you the difference between the architectures. We have a cost estimation tool, which will help you estimate the savings that you would get by moving to this new architecture. And we have a migration tool that can help you take this and move to this incrementally in a safe way. And if you think you need additional help, feel free to reach out to us at solo.io. We'd be delighted to help you.